especially the computer science world. And the first thing that happened, the first day, was some mad person came in with a big sledgehammer, knocked down all the doors of the lab, and stole all the chips from the machines. So, in fact, we couldn't do anything worse. We didn't have anything in those days. So we went. So Samson took me out. And we did all kinds of fun things. And that was great, great pleasure. And then I saw Samson again. I had another sabbatical in Edinburgh where Robin Milner was teaching me about this new funny system that he had developed called pi calculus, and particular synchronous pi calculus. And there was a postdoc there, Jean-Luigi Belli, and I were working on it, and Samson came up and gave this brilliant talk on really how to think of processes, and he had been thinking along the same lines, and so this was a great insight. I realized that some advice that someone gave me, Prakash, who said, you better really think about things quickly and write it up, because when Samson comes in, he'll write the perfectly written paper, and everything will become clear, and you'll wonder why you never thought of it that way. In fact, I've always taken that as a hero. I love talking to Samson. I've learned a lot, especially linear logic and geometry of interaction. And, one of my, which we either wrote a paper on together, and trace model categories, and one of my favorite topics is full completeness theorems, which he actually developed terminology of and spent a lot of time doing that. I should say that in the Ottawa curriculum, we at one time had a kind of a sort of opposite Bransky program. While Samson was proving these things using games, we tried to make similar, a bit of a challenge, prove the same thing using mathematical models, but almost always the games models were done first and correctly, and the mathematical models were much harder to come by, so we had to concede defeat in some cases. Anyway, today I want to talk about yet another area that Samson has recently been involved in, and this is Presheaf, quantum computing. And to some extent, this work is a tale of two students. We had two graduate students in Ottawa. Actually, one was an undergrad. Came from France. He was a student of many of us in the group. His name was Benoit Valiron. He liked Ottawa because he could talk French there. And he continued on and became a PhD student with Peter Selinger. And in some ways was influential in getting Peter all keen on the subject, quantum computing. And they wrote a series of very interesting papers, including a handbook article, a very nice handbook article, on what is a quantum programming, a higher order quantum programming, or is a quantum language. I'll mention those very briefly. And then a second student was named Octavio Malher. He was a student of me and Peter, and he, being a good student, decided he would try to dislodge both of his supervisors. So the first half was on characterizing partial choices, and the second half was constructing an open model of the system of Selinger Valiron. And that's what I would like to talk about today. The details are a little bit convoluted, so the talk will be a little bit detailed today. But the great details you'll see to some extent in the outline in the volume, and there'll be also Malher's thesis and a journal version of this eventually as we keep polishing. So let me just mention briefly, Selinger and Valiron introduced a call-by-value type lambda calculus for quantum computation. And the type system was based on intuitionistic linear logic. Now, the calculus has some built-in quantum types and terms, but really it doesn't have that much to do with quantum anything. It's really a sort of a generic, as they call it, a generic call-by-value language, but with design features inspired by quantum computing. And they stress throughout, and Peter has always said that he really wrote it for programming, not for proof theory. And that's particularly important. So it has various features. I'm not going to go into them except to mention very briefly, which you've all seen and probably know far better than I. Classical control, call-by-value reduction, uniformity of data, so it's just a linear type system that tells you when data can be duplicated or not. But one of the more curious aspects of it is this feature, implicit linearity check. And in there, so for example, when you're a linear proof theorist, we often write, you see expressions like this, especially Samson has looked at, and especially the ones at the school of Martin Highland and the students, you would say copy X as X1, X2, and you had dereliction operators and all kinds of things, and bang X for sometimes some variables to duplicate. And Selinger would just write it FX. Very simple. Duplicate variable, just write it FX. Now, there's a big price to pay for that, of course. You have to have a much more sophisticated typing system with subtypes. There's a whole technology that they had to develop, and in fact, even knowing the typing algorithm was correct was the whole thesis of that. And so it's a non-trivial thing to know. But after you've done it, you can write down, programmers can write down things like they'd like to. There's also some type isomorphisms that I'll be coming to. So let me begin then with the general story. So I think everybody here has probably seen categories of completely positive maps between finite dimensional Hilbert spaces, but I'll just mention it. So you have two finite dimensional Hilbert space, you have a notion of a completely positive map, which we've seen before in some of the talks. So there's an interesting category called CPM, the category of completely positive maps, and its objects are finite sequences of finite dimensional Hilbert spaces, and the arrows are matrices where the entries are completely positive maps. In the case when the lists here are length 1, you would just get what are called the simple CPM category. That's just finite dimensional Hilbert spaces and completely positive maps. And in general, since here you're looking at finite lists, you might think there's a general categorical construction. And yes, CPM is the byproduct completion of simple lists. So we're going to be interested in classes of operators. I don't know if the name is due to Selinger or not, but it's certainly popularized in Selinger's work on flowchart semantics. So completely positive map is a trace non-increasing if for each column J you write some trace here, the i's, you get something less than or equal to the trace of row, and it's trace preserving if it equals trace. And so then you get two interesting categories then. You get the trace non-increasing CPM maps and the trace preserved CPM maps. And these two categories are called Q and Q prime, respectively. And similarly, you can look at where the objects are lists of length 1, and then you get the simple versions of Q. So these are classes of operators, and the theorem superoperators. These are theorems that Selinger had, I believe, in his original 2004 paper. Not sure about part 2, but he suggested it's just folklore. That CPM is a symmetric monoidal category, and Q and Q prime are monoidal subcategories with binary coprimes. And now, for later technical reasons, I'll just mention, let me see. Yeah, equality is a subset of less than or equal to. Therefore, the trace preserving or containing a trace non-increasing simples, and that's a full subcategory of Q of all this. Okay, that we'll see that later. That's just super operators. So I want to talk now about what is an abstract model. So this is Selinger and Valleyrand in their end of their survey paper. They have two papers. One is an abstract, and then they have a long handbook article. They left as an open problem to try to understand what is a concrete model of the quantum lambda calculus. And they begin with an abstract model. And this model is interesting. On the one hand, it combines two paradigms. It combines the work of Benton, what I believe Paul André calls a linear nonlinear model, and together with emoji monet, all on the same pattern. So this is the framework we're going to look at. So we're going to have a pair of monoidal adjunctions, where their category here has finite products, and these two categories are symmetric monoidal closed. The left adjunction here, this one, is a Benton linear nonlinear model. And we have a monoidal comonad there. And the right adjunction here is a a strong computational monad. It's a strong monad, which is also a computational monad in the sense of motion. Bang here, the bang, is strongly monoidal. So now there's going to be two strange features. If you're a linear logician, what I'm now going to say is going to upset you. Okay? I'm going to demand that bang is strongly monoidal and idempotent. Okay, that means bang preserves tensors. So not only do you have the Sealy identity, you also have bang preserves tensors. The second is that it's idempotent. Bang bang equals well, sure. Finally, C has coproducts, and they must be preserved. And that's it. Oh, and finally, what Selinger-Valleyron called affineness. I'm going to demand the tensor unit here be terminal. And so that's what they call an abstract model of quantum lambda calculus. And I'll give an example later of an abstract model which has nothing to do. Quantum lambda calculus where Q is 0. No Q. But what we're interested really in this talk is real quantum lambda calculus. So what is a concrete model? It's going to be an abstract model where you can embed the superoperators into the Kleisli category of the Moji monad. So those are the, and moreover, it's not just annual embedding. It's an embedding that preserves tensor and coproducts. So that is a concrete model, according to Selinger-Valleyron. And they showed, of course, that the syntax satisfied this. But is there a real one? That's the question. So the answer here is that yes, there's a Presheaf version. So I'd like to talk a little bit about it. But before doing that, let me just mention some features. If we did have such a modeling, notice right away that the left monad is, the left comonad, the bang, is an adjunction between a Cartesian category of Cartesian products like we saw earlier today, and a symmetric monoidal category. So the Cartesian part accounts for classical duplicability. And the symmetric monoidal closed part here accounts for quantum, I'll call it non-duplicability. The right adjunction here gives a strong computational monad, which is supposed to account for the probabilistic aspect. Finally, those last two strange things for a linear logician say that bang preserves a tensor, and which is something like, I mean, it says something to the effect of characterizing duplicable pairs. Duplicable pairs of things. And bang bang A is isomorphic to A. This says you that the little delta of the comonad is isomorphic. So a bit odd, but nevertheless, it's fine. And finally, we're going to, by the way, if you're a category theorist, just to remark, those are the same thing. These conditions are equivalent to saying I here is strongly monoidal as a functor, and L is fully faithful. So that's fine. Maybe I'll just make a brief mention that computationally, what the idea that Selinger pointed out was that the category C and the Kleisli category of the Moji monad and the co-Kleisli category arising from the comonad of the linear logic side all have the same objects, and those are just the types of the quantum lambda calculus. And the maps are values of type B parameterized by variables of type A. So for example, a morphism A to B in the Kleisli category of the Moji monad is really a computation of type B, which is roughly a probability distribution. On the other hand, a morphism in the C, in the co-Kleisli category of the bang, is really a map from bang A to B. Now the idempotence of bang tells you there's a bijective correspondence from bang A to B and bang A to bang B, which tells you the classical values are duplicate. So that was the intuition, as far as I understand, that they have for this. So there are two stages to construct a model. One is to build an abstract model. That's rather a long thing. I think in the paper it was 8 steps in the outline paper. And then 2 more steps to actually find some concrete instantiations. So let me tell you what the story is. So the B, the C, and the D the models that we're looking for are really going to eventually be given by presheaves on a category B, presheaves, contravariant presheaves on a category C, and some class of continuous functors with respect to a distinguished class of cones, or in fact, more generally, what Fried and Kelly call cylinders. And you're going to have monoidal adjunctions, and et cetera, et cetera. So that's the general framework to try to keep in mind. So what we do is we have three parameters that we're eventually going to use. A triple of categories B, C, D with two functors like this, and a collection of cones. And the whole construction is parametric on that. So in fact, we're going to split this up into two finer things. So we're going to have this, the linear logic part, and then this part here, we're going to put the real presheaves in the middle, and then we're going to reflect down. There'll be a concrete reflection given by Fried Kelly to a reflective subcategory of gamma preserving functors. So that's the general framework. So let me talk a little bit about what's going on. So I'll try to motivate how, on an abstract level, how this arose more and more finely, and then I'll state the theorem. And then I'll come back and talk a little bit about a few more details, but I'm worried that it'll become too technical. So am I already 20 minutes in?
That's fact. We have to be 10 minutes.
10 minutes, okay, well.
8 if you want some discussion.
Okay. So the basic idea is to lift the sequence of functors like this. And the first thing is we want these things here to be a symmetric monoidal close. So we have to give them a tensor product, and so there's a lot of this talk should be sort of dedicated to Brian today. There'll be a series of theorems here that are all Bayes theorems, looked at extremely abstract theorems of Australian category theory, but then looked at concretely here. So we look at Day's convolution, and we have a tensor which we get here. In order to guarantee that, though, we must require C and D to be monoidal. That's fine. Then I want to guarantee that this is a monoidal adjunction. So how would we do that? Well, it turns out, curiously enough, if B is Cartesian, for example, we can pick for L the left cone extension. And if you pick the left cone extension, and if you demand, so here's yet another condition, if you demand that phi is a strong monoidal functor, then the left cone extension itself becomes strong monoidal. But I want this bang, remember I wanted bang to preserve tensors, so I want phi upper star also to be strong monoidal. So I'm looking for intuitive conditions to guarantee that. And if I do that, then the composite, the left cone extension composed with this phi upper star, should then be composite of two strong monoidals. So how would I guarantee that? Well, here we use the first of the Bayes things. This is only a small one, but it's important. Suppose you have, what we have to do is we say, well, it's not arbitrary phi. Phi is not only strong monoidal, we're going to demand phi be fully faithful. So suppose phi is fully faithful. Then we have this left cone extension. And if the lemma of Brian Day is if you have this isomorphism valid when the phi is fully faithful, and if phi happens to preserve the units, but I already said that phi is strong monoidal, so it definitely preserves units. In that case, phi upper star is strong monoidal. So there is some condition, sufficient condition, and this guarantees then that the composite, the bang, the linear logic part, has some of the properties we want. Phi fully faithful implies bang is idempotent. Phi fully faithful, strong monoidal, and satisfies Day's lemma implies that this thing is a composite of two strong monoidals, so bang becomes strong monoidal. That's nice. Many of the adjunctions, oh yes, tiny observation is that these adjunctions are essential geometric morphisms and toposes, and therefore both Lan and phi upper star have right adjuncts. And therefore these things are left adjoints, and therefore they preserve right limits, therefore in particular they preserve coproducts, therefore in particular boson. So therefore, finally, bang preserves the code. In fact, code. So let me, so as you can see, it's becoming a little technical, so let me at least state the theorem. So here's the abstract theorem of Octavio, which we polished a bit. Suppose you have three functors B, C, suppose you have three categories and three functors. Here's the conditions we need to get an abstract model of the quantum lambda calculus. B has to have finite products, C and D symmetric monoidal. B, C, D have coproducts distributed with respect to tensor. C is affine, phi C are strong monoidal, preserve coproducts. Phi is full and faithful. Psi is essentially surjective on objects. The day lemma. And you look at any class of cones here, gamma, or well, they're cones in D or coconuts in DR. For example, coproducts, which contain all the coproduct cones. Then you get an abstract, and we demand that tensor preserve them. So tensor must preserve coproducts. In that case, there's the model. So I have to, well, given the time, I won't be able to give you more probably.
You have 10 minutes yet because we start to do.
Okay, I'm not sure how much I want to go into some of the details. Let me say a little bit about what we're wanting to do. So this was the linear logic part, and this was this monoidal adjunction between this intermediate category, and this C is the key category, the key one for this whole discussion. Because we want to take this Moji monad, get the Kleisli category of T, and we want to embed the superoperators into that thing. So this C is kind of the center of the model, and how do we construct a concrete C is a big problem, which I'll talk about later. So we want to construct construct the superoperators. D has to be embedded into CT hat, and D should be the category of superoperators. So that tells me right away, D here should be superoperators, some kind of categories. Okay, so we need to look at this, and so for this we modify the Presheaf category, because one of the problems is that in order to get this nice adjunction property, I need a Yoneda that preserves coproducts. That's a real problem. I've had this many times, unfortunately, in my career, that we needed Yoneda to preserve coproducts. It occurs in normalization by evaluation in many subjects. And Yoneda doesn't preserve coproducts. But it does. This was the purpose, and I'm really glad Dushko, wherever he is, introduced that monograph of Lambeck, monograph 24, Springer lecture notes, and that was the first place where this was pointed out, that you don't want to look in all Presheafs, you want to look at certain ones, those that preserve these kind of cones. And if you look at say, coproduct preserving functors or something like that, then the Yoneda automatically preserves the right structure. So this was what part of the Lambeck thing, and then Kelly and Fried have this much more abstract version where gammas are set in cylinders. So what I need is a Yoneda which preserves coproducts. I think I'm going to skip. I'll come back to this. Let me just make a couple of remarks here. So this was the picture. The linear logic part is over here, and we've completely discussed that. We've done with that. But it's this other part that's the more bothersome part. And this is the one where I need to get an embedding of this into the Kleisli category of that Moji monad. And I need this embedding here to preserve coproducts and tensor. And so what you have to do is you have to get a monoidal adjunction here. You have to get, this has to be a certain class of cones. And what you have is another huge theorem of Day, which is called the Day reflection theorem. And the Day reflection theorem says that under appropriate, the Kelly-Fried theorem says that under appropriate choice of gamma, this is a reflected subcategory of this. This is the reflector. And the Day theorem says this is a monoidal subcategory with lots of additional structure. And that theorem is highly non-trivial. But you boil it down, it says that. So one has to be able to prove that this is an inclusion and that this is a monoidal, strong monoidal reflector. And that is part of the machinery of the Day Fried Kelly theorems. So let me leave that, but to mention, what you do is you pick F2 here. G turns out to be, you can calculate G, and it turns out to be isomorphic to the inclusion. And F as a left-con extension is given by a coend like this. And in order to even make sense of this, you have to assume that this category is co-complete, so you have to take enough cones, so this is co-complete, contains the representable presheaves. And then moreover, tensor has to preserve the co-cones in gamma, or tensor op preserves the cones in gamma. Okay, so this gives you some machinery, and I think I've already mentioned this is a monoidal adjunction, and you get this from using a series of properties from category theory. So, the Kleisli category inherits all the coproducts from C. This is the general theorem. And this comparison functor, this here is the comparison functor between this category and the co-Kleisli category and this. And this comparison functor turns out to be fully faithful Stroman model. Preserves coproducts. Very interesting. So, if the class gamma contains all the finite product cones, then H preserves finite product cones. So that's what it is. Finite product cones in D op, which is the co-cones in D. So, right, so that's fine. And I seem to be missing I'm missing an example. I don't know what happened, but I will quickly tell you an example. Here's an example of quantum lambda calculus without the Q. So what you can do is take V and take C to be finite sets. Identical. So the bang is the identical. Okay? No quantum. And then I'm going to take for D an interesting category. Finite stochastic REL. So finite stochastic REL is, when you boil it down, finite sets, but then all this stuff with integrals and so on becomes finite sums, and they become row stochastic ranges. Very nice. Nice category. And it turns out that this gives you a model of something. It gives you an abstract model of the quantum lambda calculus. All those theorems that I said work. But you don't, it's not a concrete one. You don't have the embedding. But, and it gives us some kind of a model, some kind of probabilistic higher order lambda.
What's the function from sets to fin set?
This is fin set. It's identity. So, so that was one model, but that's not what we're trying to do in this talk. We're trying to get quantum models. But it's a curious byproduct. You get this abstract model, or I don't know if you want to call it concrete abstract model. But then the genuine model, we need to find ourselves an intermediate category C, which has all the properties I mentioned. So what you do is you're going to construct a series of free categories. So you start with any discrete category K, and look at the free affine category on K. Okay? Now, I'm not going to take any old K, because this is supposed to be related to quantum stuff. So let K be the discrete category of finite dimensional Hilbert spaces. So then, now you have the free affine category. And it turns out the inclusion functor here into the simples works nicely. And you get free affine has an embedding into the simples. Now we use those things I mentioned before, the simples, the trace increase, the trace preserving are embedded in the trace non-increasing, and then that goes into non-decreasing. And then you go into the inclusion. And so then it turns out the universal property of we do another free construction, the free coproduct completion of the free affine. So you take a free coproduct completion of that, and then that, by definition, preserves coproduct. Aha, we're on our way. So now,
There yet?
are we there yet? Not quite. So, oh, there it is. There is the one I mentioned. sorry, there's the one I mentioned before. If B and C are finite sets, this is, came in the wrong spot. So, lemma is if you have any affine category, then this embedding from finite sets into the coproduct completion preserves coproduct. And so we replace A by the free affine category. And the final theorem is that let this category be the free affine category, the plus of that is coproduct completion. Let D be Q, the superoperators. This is a subcategory of superoperators. And this whole thing is a concrete model.